Okay, so we're kind of here towards the end of section 3, and the reason why we're doing this thing about electron configuration, and now we're focusing on the parts that are really involved in chemical reactions. Even though an atom might have lots of electrons, the only electrons that really matter are the electrons in the outer level, the S and P. Remember, the outer level only has S and P? And so these are the ones that are involved in chemical reactions. And when they form a compound, these are going to be the electrons that they're either going to lose or gain or share. Okay? They're either going to be losing some of these electrons, gaining some more electrons, or sharing electrons. All with the goal of having their outer level filled. Okay? Remember, they're all noble gas wannabes, and they accomplish this by either losing some of their outer electrons so they can have a noble gas configuration, or gaining a few more electrons so they can have a noble gas configuration, or sharing electrons so they both can have a noble gas configuration. So they're after that, you know, in these chemical reactions. And so it's just the highest numbered level. So if the most helpful thing then for figuring out how many electrons they have in their highest numbered level is that noble gas configuration that you have on your periodic table. Like for instance, if you look at sodium, which is element number 11, its noble gas configuration is going to be Ne 3s1. So for it to become have a noble gas configuration, what would it need to do? If its electron configuration is Ne 3s1, what does it need to do to have a noble gas configuration? Lose that 3s electron. So if it loses a 3s electron, then it has an electron configuration of Ne. Okay? So that's what we're talking about here, and that's probably the most helpful part. Well, let's see, let's do one more while we're at it. Let's go over here to chlorine, element number 17. Look at its noble gas configuration. It's Ne 3s2 3p5. To be a noble gas, it needs what? It needs one more electron, right, to become a 3p6. So that's what chlorine likes to do, is it needs to gain an electron from something. Well, we just talked about something that had an electron it needed to give away. Chlorine needs one. Those two can meet each other's needs. Sodium gives away an electron. Chlorine gains that electron. They both have a noble gas configuration. They're both ions, so they'll be attracted to each other and held together. That's the bond. So that's really all that's involved in that process. Okay, now these electrons that are in the outer level, that S and P electrons, are called valence electrons. We give a special name to them. All the other electrons inside, farther in on the other levels are just, they're called inner electrons or inner shell electrons, different names that they give for that. They're not usually involved in chemical bonding. Just the valence electrons, in the S and the P. So valence electrons are often located in incompletely filled main levels. Like sodium, we said it had just one S electron. Chlorine had an S2P5 in its outer level. That's pretty common. And it's good because then they can react with each other. If you already have a noble gas configuration, you don't want to react, okay? So it's difficult it's almost like you have to bribe them with energy to get some of them to react, and the only ones that we've been able to react are down towards the bottom, because their electrons are very far from the nucleus compared to some of the ones at the top. Okay, we talked about that already. Now, atoms have different abilities to capture electrons. If they need one or if they don't need one, it's going to be kind of deciding thing. Valence electrons hold atoms together in chemical bonds, like we just talked about. And in the process, one will often become positive and the other one will become negative. And what do opposites do? Opposite charges do what? They attract each other. That's the bond. Okay, that's the bond. Now, a measure of how well they attract additional electrons is called electronegativity. And electronegativity is on your chart. Okay, so it's on the back side. So why don't you use this chart and look on the back side. And the number for electronegativity is the top rightmost number. Okay, top rightmost number. Now, notice that the noble gases don't have any electronegativity. They're already satisfied. They don't want to capture any more electrons. So they just don't have a number. But all the rest do. Where do you find the highest electronegativity on the periodic table? Where do you find the highest number? Where'd you find it? Isn't it in the upper right-hand corner? Isn't it like fluorine has the highest? Mine says, what, 3.98? Is that what yours has? Okay, sometimes we round it off to 4.0, but 3.98. So that has the highest electronegativity. That means it's a measure of the ability to attract electrons. Fluorine has the highest ability to attract additional electrons, which it needs to become a noble gas configuration, right? Okay, now where would I find the lowest, do you suppose? Kind of the opposite bottom corner, right? Down in the bottom left is where you find the lowest ones. They have the least attraction for additional electrons. Why? They would rather get rid of their electrons. Okay? They'd rather get rid of their electrons to get back to a noble gas configuration. They have like too many. Yes?
Why do like, what are they called? Krypton and xenon have like, the negativity, but the rest of the gases don't?
Because, you have more than just xenon. Mine only has xenon. You have, which one is the other one do you have?
Krypton.
Krypton also
It
has
says
one?
3.
So which means that they have been able to force it to react. And because of that, we can measure then their ability to attract additional electrons. Okay? But notice it's not real high. I mean, it's kind of more towards the middle, I guess I would say. So now let's just quickly go through the trends yet. As I go down or go across the period, what's happening to the electronegativity? As I go from left to right, what's happening to it? Going up, okay? As I go down a group, what's happening? What's happening? Electronegativity as I go down. It's going down, okay? It decreases, okay? So you see the pattern. So the alkaline earth, the alkaline metals and the alkaline earth are going to have the lowest numbers, kind of as a group. And we're going to have those on the other side over here are going to be the highest, like the halogens are going to be the highest as a group. And we won't do that. Now, then the rest of of that section is just talking about D block, what's happening in the D block. The properties it says of the D block metals don't really vary a lot. Not as much as these did right over here. And you can go through all the different, what's happening to the radii. You can use your periodic table to answer those questions. Okay, so let's see if there's anything else that would be of help to us for our assignment. I don't think so. I think that was pretty much it. So that's what I didn't get covered yesterday, and I thought it might be helpful.